Welcome back. Today we have a quill of a Flot TB15 drill press on the bench. It's a fairly small drill press, but rather nicely made too. This is the quill, along with the spindle, with the spline drive in the back. And these small drill presses don't have a Morse taper. They have an external taper on the spindle, which is a B taper. B tapers are basically the same size as a Morse taper. This being a B16 is the short end of a Morse taper 2. So this is a B16 drill chuck. This fits on here, but it would also fit on the back side of a Morse taper 2. So that's the taper here. And this was sent to me to have a look at it. First of all, checking the run out here, check if the shaft is bent, check the bearings, and do what's necessary to get it back in a good condition. So let's get this on the measuring table and confront it with an indicator. So I have a Mitutoyo Hicator, which reads 1 micron per increment, and my height gauge, and the quill sits in a magnetic V-block. This is just for convenience, so it's easier to work with it. Okay, this is the run out on the extreme end of the B16 taper. This starts at about -40 and goes up to +40. That's micron. So we have a total indicated run out of 80 micron. That's a little bit much, and there is a strange divot here. I can't show it, but I can tell you that the bearings in this unit feel a little bit crunchy too, so we have to do something about that. We're going to exchange the bearings before we do anything else to the spindle. Okay, we have rather bad run out here, almost 0.1 millimeters. Let's go further in. I like the height gauge for the precision indicators because it has a nice fine adjust. Okay, let's start at -40 again. Okay, -40, almost 10. Hard to tell because the surface on this taper is a little bit buggered up. So we have definitely run out in the whole taper here. And this, if you add a drill chuck on here and a drill, you would have a horrendous run out the end. Let's check the spline shaft to see if the whole spindle is somehow bent. So let's go in this area where we don't have the splines cut. Okay, that's way better. That's better than 5 micron. It's pretty decent, considering the bearings in this quill not being in a very good condition. Let's drop it down. Here we are in the spline section. So we have to be a little bit careful not to bump the indicator like crazy. But these Hicator, or if sold by Marcator, are surprisingly robust precision indicators. Okay, we have about 10 micron here. Let's go to the extreme end of the shaft, just for fun, but it doesn't seem like the shaft itself is bent. 0, 20, 25, 25, 10, 0. Okay, 25 micron on the end of a spline shaft on a spindle with shot bearings, which is only a drill press spindle. I'm not concerned here. This looks good to me. The splines in the spline hub have some give too, and it's okay. This should be absolutely no issue. But this end of the shaft, this is definitely an issue. This has to be addressed. Once we have the spindle out and change the bearings, we will set this up on the surface grinder and regrind the taper to a very high degree of precision. So next we have to check what bearings we have in here. Oh, damage assessment. What I think happened is either a workpiece catched with a drill or the drill chuck got bumped during transport or something like that, and the end of the shaft, the end of the B taper here has been slightly bent out of shape. Not much. I checked around here too, very close to the bearing, and it's not measurable. So it's also in the 5 micron range, just like on the other end of the shaft here. So as far as I can tell, only this end here is bent. This thread on here is for a jack nut. You have when you have the drill chuck on here, you would have a nut here that will allow you to push the chuck off the spindle end if you want to change chucks, which is nice because otherwise you would have to use 2 wedges, 2 split wedges. This is way more elegant. But in the process of regrinding the taper, we will lose a little bit of this thread here. Okay, let's see how we... it seems like the spindle is a fairly basic setup with 2 radial bearings, which also can take axial forces. There is a misconception about radial bearings, standard skateboard bearings. They take primarily radial loads, but they can take, or they will take, about 1/3 of the radial loading in axial direction. And like in this case, you can preload them against each other. This is a nut with a safety screw here, and this preloads the 2 bearings against each other. Most spindles of the small mini lathe, the 7x10, 7x12, or the mini mills, not the Haas ones, the smaller, the Seek ones, are built with a very similar spindle arrangement. By the way, the spindle of my MCO lathe is basically the same setup. 2 bearings preloaded against each other with a nut on the end. A very basic spindle design, well proven, and it works. So let's get the spindle apart here. Okay, we have a slotted clamping screw, which is not very tight in here. And also this nut is not very tight on here. This comes off. And now we need to get the spindle out. This will probably end up with some knocking onto the end. So the spindle came out rather easy. Not a crazy tight fit in there. Okay, here the front bearing. This is part of the spindle shaft. This is a cover which protects the front bearing against dirt. And the bearing we have in here is a 6202 with shields on both sides, metal shields. And the other bearing, this is the second bearing. This is a loose sliding fit in the quill housing. This is a 6002 made by SKF in France. Very nice, but also very crunchy. Holding it up to my microphone shouldn't sound like that. Okay, the rear bearing slid right off the shaft, but the other one was a pretty tight press fit on here. I moved it back I made a ring that fits over here, but was a little bit smaller than the bearing OD. This ring has 34.6 millimeters. The bearing had like 35 millimeters. And I was able to push the bearing back in this area. And instead of hammering it over the second bearing seat, or pressing it over the second bearing seat, I decided to cut it in half. With a cutoff wheel, that's the most non-intrusive way of removing a bearing. Hammering or pressing on a shaft is always a little bit dangerous because you always can bend it. Cutting it with a cutoff wheel has, of course, other dangers, like cutting into the shaft, but if you're careful, leave about 0.1 or 0.2 millimeters and then just use a pair of pliers and you can crack it. It breaks apart. Especially on the inner ring, that's a good technique. You can see the break here and here. So now we clean the shaft, and what I didn't notice, this piece here is not part of the shaft itself. It's a sliding collar on here. So I could have also used this to press off the bearing or hammer it off. I didn't notice it when the shaft was still in one piece. But now it is off. It lost its bearings. I ordered the replacement bearings, SKF, made in Italy. This is the 6202, and this is 6002, also made in Italy, as indicated by the laser engraving on the bearing. 2C, that's a non-contacting metal seal, so these don't get hot. The rubber or plastic sealed bearings, those are contacting seals, and those create friction and heat. These also create a little bit of heat because the grease moves between the shield and the ring, and that creates also some heat. First we need to clean it off from the abrasive dust that we created when we cut the bearing in half. So this piece here slides right off all the way. We do not forget to put this back on before we press the new bearings on. That would be rather tragic and hardly very annoying. One more thing we're going to do is we're going to wire brush the thread here because it has some burrs, and we'll clean the whole shaft either with steel wool or fine Scotch-Brite. I tend to go for steel wool here. Some 4/0 steel wool. Cut a nice little piece off. Don't tear it. Yeah, that's my abrasive scissors. These have to take a lot of beating. So a little thing about steel wool. Of course, it has a fiber structure that goes this direction. And when you use the steel wool in this orientation, the fibers don't do anything. You want to go 90 degrees to the fibers, because the fibers have a very sharp-edged structure to them, and it works only in this direction. And this is a super mild way to clean pieces or parts. You can go this direction too and spin it. This also has a good cleaning effect. Or spin it in a lathe if you desire. This is really just for cleaning. This doesn't remove any material, hardly any material. I wouldn't even bother to measure the shaft after this. That looks already way better. We will hit this relieved area in between here with some medium grit Scotch-Brite because there is some staining and rust on it. that we don't want to put back in the quill when we assemble it. Yeah, putting it in the lathe would be the right call, but feeling a little bit lazy today. This is a rather hard steel brush. Clean the spline drive with this. This is a Kratex stick. So just when it's put back together, there are no burrs or anything that might give problems. I think we're going to put it on the lathe anyway and run the bearing seats with some precision ground flat stones. I don't trust these. This one has a small dinkly dink in some here. Here is a small dinkly dink with something hit it, not me. We're over on the lathe. We're using some isopropylene alcohol to degrease the bearing seats before we use the precision ground flat stone. When you use these on a round piece, they will take away material. You have to be super careful, but the results are usually excellent. Let's check our diameters here just out of pure interest. So this is nominal, slightly plus. 4 microns in plus. 1 micron, slightly tapered too. And this one, I guess, is a little bit undersized. Yes, it's 4 micron undersized because the bearing was a sliding fit on here. And while we have the part spinning, we can also use the Kratex to clean up the thread here. The Kratex will wear itself into shape of the thread and chase the thread. Careful, this can be reasonably dangerous. But I expect my viewers to be able to assess dangers by themselves. I hope I don't need to tell each time I'm doing something dangerous that it is dangerous. I will point out non-obvious dangers, definitely. This is just a drill press spindle, not a mill spindle. We don't need to go full on. We'll just do good practices. Here's the bearing. When you put a bearing on, mount it in a way so you can read the laser engraving in mounted condition. The laser engraving usually is only on one side, and we'll have this ring here, and we will have the bearing put up against it. And if you put it on like this, you cannot read the engraving because on this side we have this ring. Put it on so you can read the engraving. Just a little very practical tip. I have a lab hot plate here. These are super useful in the shop. I use them to cure glue, for shrink fits, for annealing and tempering small parts. It even holds the coffee warm, so super useful. Goes up to 350 degrees C. Fresh piece of aluminum foil, a clean bearing. So I put this on at about 120 degrees C. So 100 degrees C is what most bearing manufacturers recommend as a maximum when you do a shrink fit with bearing. Okay, bearing is hot. I had it soak for about 7 or 8 minutes at a little bit of 100 degrees C. And I have the spindle and vice vertical. I have to pass 2 bearing seats. First the thread, bearing seat, and then I want the bearing to go on here. I have gloves on. I have 2 gloves on because I don't want to burn my fingers. And my heavy welding gloves or my thick gloves are just too thick to get a good feel. So wearing 2 pairs of nitrile gloves, getting bearing on over the first fit and then on the second fit. I have a pipe ready and a simplex hammer. Okay, here we go. First seat, second one, and there we go. That's perfect. That's always a little bit exciting. It's really, you can get stuck here if you are out of square, and then you usually are in trouble. The right thing would be to try to get the bearing off as quickly as possible. Next we will take something out of Robin Renzetti's book of spindle building. We will put some rust preventive on this clearance surface here, just so it doesn't rust. And before we continue, we will also clean the quill. This has seen some things in its life. Next we have the quill, which I cleaned, and I put some LPS3 rust preventive on the inside, on the clearance surface here, and also here on the clearance of the shaft, so we don't get any rust issues. This should go on as a sliding fit, I guess, or not. Okay, we'll put this on the hot plate so it goes over nicely. There is basically no other way now to mount the quill other than heat, because if we hammer the quill on, we definitely put load on the balls inside the bearing, because the other race is not supported by anything other than the balls. But that's what a heat shrink or thermal expansion is useful for. Okay, the quill heated up nicely. Now it should go on without a problem. There we go. Of course, we have a little bit of weeble wobble up here because it's a non-preloaded bearing down here, single bearing, and those have play. That's counteracted by adding a second bearing on top here. I'm going to heat the rear bearing a little bit and also the housing a little bit. So the bearing is definitely a loose, easy to go into the housing, and also a sliding fit on the spindle. Okay. We are heating the quill housing with a butane torch. Could also use a hot air gun. And in a second you will see me use a temperature stick. It's a crayon that changes the color at a certain temperature. This is a 100 degrees C stick. It's a Faber-Castell thermochrome. And this gives me a good indication when the quill is at a certain temperature. And 100 degrees C is something I deemed a reasonable temperature. Okay, heated the quill housing, the bearing is hot, and here we go. Yikes! Hot, but it's on. It's perfect. It can happen that you burn yourself doing this, but bearing went on without any beating, hitting, or something like that. And yes, this quill has seen some use, but in overall it's still in good shape. It has some ding marks, some scratching, but it's an old machine, it's a used machine, and now with the new bearings, and once we have reground the taper, it will be in excellent condition. We have to make sure that we don't mess up the bearings during grinding with grinding dust, so we're going to put on a little bit of a cover on here. I got the quill on a magnetic V-block, and I have my indicator stand with a 2 micron indicator touching the end of the shaft. And I put a tiny bit of preload on the nut here, just with a spanner wrench, a pin spanner. And I'm basically just checking the end play. Double checking if my indicator is touching. Make sure it's seated. And I'm pushing on the end of the shaft on both sides. And there is basically no end play, no measurable end play with this indicator. So I deem that good enough. And yes, the indicator is really touching the part. So there is no measurable end play. Get the indicator stand off and out of the way and go for the run out. If there was end play, I would very carefully adjust the nut and back here until I could not measure end play anymore. Then add a tiny fraction. This is a spindle without a spacer on the inner rings, so the preload is only defined by how much you tighten this nut. For a drill press spindle, that's in my mind perfectly fine. That's quite a convoluted setup here. I have, this is the quill with the spindle held in a toolmaker's vise, in a grinding vise. There are a bunch of 1, 2, 3 blocks on the back here in the magnetic chuck to space the vise off the back rail parallel. And also I added 2 C-clamps to pull the vise against the blocks, because the vise is hanging over the magnetic chuck and I don't want to be in danger of losing magnetic grip and have the vise drop down together with the quill. Then I have a fixture plate with a 20-40-60 block. That's a shop-made block with Rensetti-inspired hole pattern. And I have a hacked apart cordless drill bolted on here. This is a 3D printed flange that's glued to the end of the front end of the cordless screwdriver. And I have a pulley with a 1/4 inch hex shank, 6.35 millimeter hex shank, and a O-ring, a rubber belt that drives the quill over here. And I have a pulley that's held with a screw on the spline, just tightened down by hand. And when I run the cordless drill, ta-da! Cylindrical grinding, or in this case, tapered grinding. Yeah, that's the setup. I need to clean up the electronics of this thing. I have a momentary switch. This is the original one from the cordless drill, but I also bypassed it with a toggle switch, so I can run it continuous. I'm setting the taper angle by tilting the quill in the vise, and I'm just tracing the taper here with a 2 micron indicator to get it close. I will talk about that in a second, because there is a trick to get it very close, even with a bent taper here. So yeah, that's the setup, and I'm going to put a 80 grit aluminum oxide wheel on the spindle, dress it, and we're good to go. So you can see that we have a high spot and a low spot. That's the extremes of the bend. Would I use this to indicate the taper? No. I would go right in between of those two extremes. 60, let's zero this out. We have a finer just here, so we can zero it out. So we have 0 and 80. Let's go right in between. That means that the bend is now laying on its side. That means if I indicate now on this taper along its length, I will get a pretty good, I'm going to match the taper pretty good. Not perfectly, because as the taper is bent, I'm still dropping off along the curve, along the bend. And also you want to indicate on top dead center. Otherwise you're asking for trouble too. Okay, that's with the bend sideways, and now we can traverse back and forth and see how we are. So we start at 40 here, crank out, we have a little bit of a ditch, and we go back almost to 40. So there's a little bit of a weird effect in there, but it could be the damaged taper. But basically it's almost 0, 0, 0 end to end. And that will be very good to begin with. Now we can tighten the vise down mildly. We don't want to egg shape the quill. I have a wheel dresser back here on this fixture plate, and vacuum attachment here. We have a nice wheel dress, 5 micron last depth pass on the wheel, and fairly quick traverse back and forth. Wheel feels nice and smooth, but it should cut nice and freely. I added this tin foil in front here. I will move the camera in a second. I added the tin foil so the gap between the large washer and the quill housing is covered by the aluminum foil. Another thing, I need to position the wheel in this direction quite well under the grinding wheel on center line. With a steel scale between the wheel and the round part, you can get a pretty good idea on when you're at center. Okay, that's pretty good. I'm putting some felt marker on the taper. This helps me to identify the progress in grinding, and also it gives me a rough idea how the damaged taper is shaped after I took a first pass with the grinding wheel. It would be better to plunge down with the grinding wheel and then traverse out, because this way I'm wearing the leading edge of the grinding wheel and I cannot get all the way into the shoulder. But in the end I had to redress the wheel and this wasn't a problem anymore. Okay, here you can see very nicely where the taper already cleaned up and where we still have to go. Shouldn't be too much, what we have to take off. As you can see, it almost cleaned up so far. It's still cold to the touch, not much heat input. We took very light passes. The surface finish will need some more sparking out. I'm just traversing to clean it up right now. But now I need to move the table over and check with a drill chuck if my taper fit. In some cases it's necessary on these flat TB spindles to shorten the thread back here, because the taper goes back too far after regrinding. This thread is for the nut that pushes the chuck off the spindle. Okay, this feels very promising. I need to glue the taper and check it again, but this feels very good. And we almost have enough thread left, enough taper left. It's a hard call if I'm going to grind this little bit of galling out or not, but I'm very much inclined to leave it like that. I decided to grind the taper until it cleaned up. I didn't want to deliver a spindle with that has been reground with damage in the taper. So I'm cleaning off the taper, and that also meant that I had to shorten the thread behind the taper, pulling the taper back a little bit more to give the chuck room. But in the end, that was not a big deal. I just moved over the grinding wheel and plunged down until I hit the taper, and then I blended it all together. This heavy material removal also meant that I had to redress the grinding wheel definitely before I did my final spark out. This is my final pass on the taper. I redressed the wheel, and now I'm just traversing back and forth until the sparks basically disappear. Let's take some dead Smurf and check this for fit. Dicam High Spot Blue. I like the Dicam High Spot Blue for tapers because it prints excellent. And remember what I said earlier, the B16 taper we're grinding here is basically the short end of a Morse taper 2. So here is an old Morse taper 2 taper wiper. We take that, put a good amount of the Dicam High Spot Blue on here. And then we take a good chuck with the matching taper, and we use the taper wiper to blue the inside of the chuck. Then we go here. I clean this with alcohol. This goes on here. I press it on, and I turn it only a tiny bit side to side, like this, maybe 5 degrees side to side, and I wiggle it back and forth. And this gives me a realistic print. As you can see, we have a full band of contact here, and probably on this side too. So you turn this like 5, 10, 15 degrees side to side, and then you take the chuck off. Then you get a pretty realistic impression of the fit. And the heavy band down here, this is where the taper ends, and that's where a lot of the high spot blue, that's a tough word, collected. This is this dark band, and we have up here a band that's blank, that's not touched by the taper. That's the inside of the chuck where the taper ends, where the taper is not ground any further into the chuck, and it continues cylindrical. And in between, this is where the taper hits. That's not terrible. I'm not going to touch this anymore. This is good. This is really good. Let's get this on the bench, check the run out. I checked it already here on the machine, and it's really good. But let's go to the bench and check it there. Now is a good time not to drop the spindle. Okay, we're back at the bench, or better the surface plate. Put the quill back in a magnetic V-block. I have the 1 micron indicator here, and let's check the run out. Ooh, yeah, that's like 1 micron. Let's say it's 1 micron, just to make people happy that there is an error. Maybe 2 micron on a good day. Here out on the other end of the taper. Yeah, same result. Pretty darn good. This is probably better than factory on this drill press spindle. I love this stuff. Things like this are way too much fun. So there's a person who has a very old Flot TB15 drill press. It's a very good machine. It's a small, good quality, made in Germany drill press, but somebody buggered up the taper of the spindle and made the machine virtually useless except for maybe woodworking. But the TB15 is way more than that. And now with a little bit of work on the surface grinder, I got this spindle back into spec and probably better than original spec. And also we changed the bearings. It's turning super smooth without any side play. I'm very, this is something I can ship without being worried. So only things left to do is to needle file the end of the thread here where I plunge down with the grinding wheel. That's the only thing. But apart from that, it's done. Clean it, oil it, put some rust preventive on it and ship it. So I hope you enjoyed this rebuild of a Flot TB15 drill press, spindle and quill. Quill is basically a spindle housing that can move in C direction. I hope you enjoyed. Thank you all for watching and I hope you learned something. See you next time.